Okay. We're going to be learning how to do a definite integral that involves substitution, which is the single most common type of integration you could perform. So let's start with something we already know how to do. So let's start with a fairly simple integral. Let's say we have 2x cubed plus 1 to the 4th power, and we're going to multiply that by x squared dx. Okay, this is not a definite integral, not yet. Now, I could multiply this whole thing out. That would be very inefficient and it would take me a long time. And in fact, if I multiplied the whole thing out and then integrated, I'd still want to factor it back together again. So we all recognize this is beautiful. If 2x cubed plus 1 is my substitution, because that's my argument, then that looks a lot like its derivative. So of course I would say, let u equal 2x cubed plus 1, then my du is 6x squared dx. Okay, as long as I have the x squared, I'm okay, because I can introduce a constant multiple. What I cannot introduce is a variable multiple, because that would mean I'm putting variables in and out. That cannot be done. So I will simply put a 6 and a 1/6, and now we're good to go. When I make that substitution, this becomes 1/6 u to the 4th du, which we know is going to now be u to the 5th times a 5th. So that'd be 1/30th u to the 5th plus c, and finally 1/30th 2x cubed plus 1 to the 5th plus c. Beautiful. That was a piece of cake. So what's different today? Well, today what I want to do is I essentially want to do the same problem, but I want to do it with limits of integration. So let's suppose now I give you limits of integration. Let's keep it simple. Let's suppose our limits are from 1 to, how about 1 to 3? I'm going to give limits of integration from 1 to 3. Well, here's something that I know is true. I know this is the antiderivative of the original problem. Forget the definite integral for a moment, the original indefinite integral. Now, the difference is an indefinite integral has no limits of integration, so its answer is always a function, and that answer is called the antiderivative. A definite integral is a scalar. The final answer is just a number, a scalar. So you don't say the final answer is the antiderivative, you say the final answer is the antiderivative then evaluated. So I know no matter what, now because we're doing a definite integral, I don't need the plus c, or in other words, I get to choose my plus c. So the answer to this question, I'm going to put it over here. The answer to this question I know is 1/30th 2x cubed plus 1 raised to the 5th power evaluated from 1 to 3. I know that's the answer because I know this is the antiderivative. And in a definite integral, remember, all values of c produce the same final answer no matter what in a definite integral, because you're subtracting it from both ends. That's why in a definite integral, you actually get to choose c to be 0. Most people tell you just ignore the c, drop the c. No, actually, it's because you're choosing c to be 0. If you wanted to choose c to be 5, great. But then you have a plus 5 minus something with a plus 5, and then your 5s would cancel, and it's just extra work. So now my final answer here would be 1/30th. Now, if I put a 3 in here, that'd be what? 27 times 2 plus 1, that'd be 55. If I put a 1 in here, that'd be 2 plus 1, and that would be 3 to the 5th. Oops, I put the 3rd power, sorry. 55 to the 5th power minus 3 to the 5th power. Yikes. Now that's a big number, so let me go ahead and calculate that. Huge number. So right now, make sure I got this right. So my final answer looks like 251,642,066/15. That's a really big number, okay? But that's the answer. Okay, I don't care that it's a big number. It makes sense it's a big number. The question is there a more efficient route from getting to here, from here to here? And that's what we're going to learn today. Now I'm going to show you what most people do, and it is incorrect, and I don't want you to ever do this. So I want you to watch but not write it down, basically. Here's what most people do. In fact, this is what all students do if left to their own devices. When I make this substitution, notice the limits here from 1 to 3 for x, I transferred down and said the limits from 1 to 3 to u. Now, that is not correct, but that's what people do. So now let me take this away because I don't need this anymore. A definite integral is a numerical answer, period. And all your goal is to just give the numerical answer. So right now, this definite integral has a numerical answer. It's equal to this definite integral evaluated from 1 to 3, and that would be 1/30th, 3 to the 5th power minus 1 to the 5th power, which would be 242 over 30, or 121/15. Houston, we have a problem. We know this is the answer. This can't be the answer. In fact, this is kind of puny compared to that one. Why did I get different answers? Because these are the wrong limits of integration. These are the limits of integration for x. We say, well, can't I just change it back? No. Here's an absolute mathematical statement that people violate all the time because nobody told them otherwise. In a definite integral, you don't ever, when you make a substitution, you don't change back to x. There's nothing to change back to. A definite integral is a numerical answer. So you're saying it equals another definite integral that is a numerical answer. So I need it to be equal to this. And here's the mistake. These are not the limits of integration. These are the limits of integration for x. So if I'm doing a definite integral and I am changing the variable, then I must also change the limits. Right now, the answer to this question is this, and this is incorrect. I don't change it back to x because this is a number. You don't say, let me solve the problem. I got 3. Now let me change the number 3 to 8. But what? Numerical values cannot get changed. Substitutions can happen, but numbers can't change. So the question is, how do I justify this? Well, go over to here. I know that's the answer. So the way we justify it is go to your substitution. And what did you say? You said u equals this. Now, x is a value, we can write it like this. X is going to range between 1 and 3. Okay. Or you can simply, I have x equal 1, I have x equal 3, and I'm evaluating both. So technically that just means x is between them. What would happen to u? Well, technically u is a function of x. So u of 1 equals what? 2 times 1 cubed plus 1, that's 3. U of 3 equals 2 times 3 cubed plus 1, that was 55. So therefore u will range between 3 and 55. Okay, I'm doing scratch work off to the side. My preference of representation here is when I make this statement and then I make this statement, at this point in the problem, I will now change the limits of integration because the x limits from 1 to 3, I need to change into the u limits, which will now be from 3 to 55. I found the simplest way to do this is I write it like this. I say, as x ranges from 1 to 3, u ranges from 3 to 55. And so what do I do? Right here, I write from 3 to 55, which means at this point in the problem, this is ranging from 3 to 55. So my answer is 1/30th, 55 to the 5th power minus 3 to the 5th power, which should look like exactly what we did over here, except that we got there in exactly half the steps. From here to here took half the work of the original problem because there's no changing back and solving the original. Now, what I did at first was I did the general antiderivative, gave that as an answer, and then we evaluated that. That is absolutely correct. You can do that 100% of the time, but it's also very, very inefficient because it essentially means you're doing the entire problem twice. once with X and once with U. So what I'd rather do is say, I'm going to change the variable. Can you tell me the definite integral that it will equal to in the new variable? Yes. These limits here were replaced by these limits here, which means that the numerical value that this integral is going to produce is equal to the numerical value that this integral is going to produce. And because they're equal, the moment I'm done, I'm done. Now, I will use my calculator to evaluate that. There is no changing back because there's nothing to change back to. This is a number. You do not substitute numbers for other numbers. That doesn't make any sense mathematically. So we're going to do a bunch of this today. And like I said, the number one problem I see in the upper level classes, and I mean past Calc 1, is that people never learned how to change the limits of integration. So they'll actually report multiple numerical answers to the same problem. That's dangerous, right? At the end of an algebra problem, you never said X is 3. And 3 is also equal to 6, which equals and 0 and infinity while we're at it. No, a numerical value is not equal to another numerical value. That makes no sense. So let's try another one. Let's suppose I have the limit. Let's keep it simple. 6x squared about minus 3x plus 1. And whoops. Let's say 4x minus 1. And we're going to go from, how about 0 to 1? Okay, this is not a difficult problem. This is a fairly simple problem. So we want to walk through this. We want to navigate through this correctly from beginning to end. So I want to show you all the process, because we should be able to completely do this problem in only one more step than the indefinite integral would have taken. In other words, if I remove the limits of integration, we know exactly how to navigate through this problem. Doing a definite integral shouldn't take longer. It should actually be less work because there's no substituting back. I have an additional step because of the numerical values changing, but because I don't have to substitute back, I also eliminate steps. So we'll start like this. Let u equal 6x squared minus 3x plus 1. Then du is 12x minus 3 dx. I don't have a 12x minus 3. But you know what? This is also 3 times 4x minus 1 dx. Now, I'm not doing anything. These quantities are exactly the same. I just factored out a 3. I'm not moving anything to the other side of the equal. That's not a legal step. So I need an additional 3 here to make this work. So first thing I'm going to do is I'm going to multiply that by 3 and then by 1/3. So now I have exactly the chain rule factor that I need. Okay, that's the first thing I need. Next thing I'm going to do is change the limits of integration. So currently, right now, the limits are 0 to 1. Now, of all of the things you will ever do the rest of your life in mathematics, this is absolutely the easiest thing you will ever do the rest of your life in mathematics. And 99.997% of the time, you can simply do this in your head. You don't even need a calculator. It's rare that you would even need a calculator for this. What I'm going to do is replace x with 0. I get a 1. Now I'm going to replace x with a 1. 6 minus 3 plus 1, that's 4. That's it. That's how much work is required, absolutely 100% of the time, to do this. But because I did this, when I now write my new integration, this is of the form, because there's my du, this is of the form 1 over u du, and my limits of integration are 1 to 4. And I mentioned this when we were first doing the substitutions. When you do a substitution, it's all at once. It is not mathematically possible to have the old and the new, the x and the u coexist at the same time. I can't mix them up here. I can't mix them up here. There is no such step that exists. A lot of people do that and they claim somebody showed them. I always pray that you didn't pay that person money, because mathematically that is the single most invalid thing you can ever do. So don't do that. This numerical value we're claiming is equal to this numerical value. Okay, that's a fairly simple claim, but looking at this, there's nothing about that that's intimidating. That looks really, really simple. So let's continue. So this is 1/3 natural log absolute value. And that absolute value actually is quite important. Until I evaluate it, I don't know if, what I'm going to get. Okay, so I write it like this. Now, because this is still fairly new and unexplored territory, just a reminder, you always evaluated it the top first, and then you subtract the evaluation from the bottom. Sometimes people get those backwards. So now I have 1/3 natural log of 4. I don't need to say absolute value of 4 because that's just 4 minus natural log of 1. I like this answer. Anybody? What's natural log of 1?
0.
0. Yeah, we love log of 1. In fact, log any base of 1. So that means my final answer is simply 1/3 times the log of 4. Now, that is the answer. Can I manipulate this? Can I do things with this? For example, we know that I can go this way. So reverse abominable snowman. Because this way it's, can I move the 1/3 up here? Would it be legal to do this? Is that illegal? What do you think?
Yes.
And then I probably do that. Cube root 4. The question, that's legal. The question is it better?
No.
I personally, I think this would be easier to work with. If I got to evaluate this on my calculator, we all agree that this is a little bit more work to enter into the calculator. I mean, cube root, and I would say leave it like this. This is correct. This is correct. This is correct. Leave it like this. I don't see any advantage gained. Now, if this were an integer value, maybe an integer, let's say that was a 2. Well, log of 4 squared is log of 16. I don't see any problem with that, but I'm creating an icky argument here. I just don't see where that is going to be an advantage to me. The potential for error is there. So I just say leave it alone. Now, this process was fairly simple, and there's nothing about this problem really should tax us. But here's what I see. If I ask this question, or this comes up in Calc 2 or Calc 3, here's what I'm going to see people do. Now, I don't want you guys to ever do this. I'm going to see the following. Now, before I do anything else, does anybody see a potential problem here? Yes, it's the wrong answer because I didn't change the limits. There's nothing wrong with my original question. Does anybody see a potential problem here? I have a limit of integration
with the U in the bottom.
I have a limit of integration that makes that undefined. In other words, right now, this is a DNE. There's nothing else I could write that even matters because anything else I write now is just utter garbage. But this is what I'll have people do. Log 1 minus log 0. Now, we all know, right, that Chuck Norris knows how to divide by 0. I actually taught him that trick. If you learn that trick in an upper division complex analysis class, I'm actually telling him the truth. You learn how to do that. So dividing by 0, that's just a parlor trick. But even Chuck can't take the natural log of 0. That's the one thing that's beyond Chuck. Yeah, I know he can count to infinity and all that stuff. I taught him how to do that. You just count by 5s. You get there really fast. But you can't take the log of 0. Mathematically, that's one of the very few things you can never do. Okay. So he doesn't sleep, he what? Oh, he waits. Okay. So this statement here is impossible. And let me change it back. No. This is impossible, and this is a DNE. Again, it doesn't matter what I write after. And getting the right answer at the end is almost worse because now I'm saying I have multiple answers. No, I can't do that. I can't do that because it changes everything. So this step here. Now, let me go back. Let me go back to the first way I did the problem because I'm going to show you something. It is always legal. So what you can do, and by the way, in the upper level classes, sometimes you have to do this because of the complexity of the problem. So what we often do in the upper level classes is we will do, this is always legal. We will do the general antiderivative, not a definite integral. I'm not saying these are equal, they're not. This is a numerical value, this is a function, but this is going to be the work. So then I will change this. Now I will come back to this and put, this is where the equal sign will be. And I'll say, and this equals 1/3 natural log of this quantity here evaluated from, sorry, 0 to 1. Which is now 1/3 times the natural log of 4 minus the natural log of 1, and that's 1/3 ln 4. We already knew that. This is absolutely legal, and I have not said anything incorrect. The only equal signs I have, this is equal to this. These are equal. This is sort of off to the side. I found the general antiderivative, and now I'm coming back to the original problem. That is absolutely legal. You can always do that. But it takes exactly twice as many steps. See, when I changed the limits of integration, I was done on the third step. You see, it's way more efficient to do this. This is legal. And in fact, like I said, in the upper level classes, when you have multiple complexities going on within a problem, sometimes it's easier to do it this way, even though it's not efficient, just so I don't get lost. So I want you to know there's always two routes. Do a general antiderivative and then come back to the problem, or change the limits when I change the variable. I want you to learn this because it's by far the fastest, the easiest, the shortest, and it's always correct. But like I said, you're never going to run across a problem in Calc 1 where this is efficient. In Calc 2 or Calc 3, there are problems that exist because of the nature of the substitutions. Okay, so let's keep going. All right. So let's suppose we have something like this. I've got the integral of cosine of e to the negative x over e to the x. Make it nice and evil here. And again, let's say we're going from 0 to 2. Big yikes. Okay. I've got a quotient here. I don't like quotients. I'd really rather be a product. But before I even start worrying about the fact that I have a quotient, does anybody want to tell me what is the only choice I have for my u?
E to the negative x.
That is correct. And the reason, it's because my argument is not just x. Okay, if my argument is just an x, I have x to a power, I have the log of x, I have the sine of x. That's not where your substitution comes from. But I have the cosine of a function. That's where my substitution comes from. And then hopefully we have the chain rule factor. So what's the derivative of e to the negative x?
Negative e to the negative x.
Beautiful. Now, do I have one of those? Yeah, it's sitting right there. See, I put an e to the x on the bottom, but if I bring it up to the top, is everybody okay with that? See, beautiful. Now, I'm not quite there yet because we need it to be negative e to the negative x. So this is how easy that is. I make that a negative, put parentheses so it doesn't look like you're subtracting, and I make that negative. There's my compensation. I multiplied inside by -1, I multiplied outside by -1. Now it's perfect for substituting. I now have it in the form cos u du. Absolutely perfect. But before I do the substitution, I need to figure out now what are my new limits going to be. My previous limits went from 0 to 2. My new limits are going to be what? Well, if I replace x with 0, then I have e to the -0. Well, that's just 1. If I replace x with 2, then I have e to the -2, which is goofy looking. And you can certainly write 1 over e squared. That's fine. So what do I do with that? Well, these are going to be my new limits, my new digs. So I'm going to go from 1 to e to the -2. Cosine of u du. Don't concern yourself with the fact that your limits are ugly. Okay, that's not even relevant. Concern yourself with the fact that now I have an easy integration. That's all I care about. So when I integrate this, what is the antiderivative of the cosine? The antiderivative.
The sine?
Is it the positive or the negative?
Positive sign.
It's the positive sign because the derivative of sine is cosine. Remember, the easy way to think about it is what function, when I take its derivative, will give me this, and that would be the positive sine of u. Now I slap that negative. That negative comes from here, from 1 to e to the negative 2. So my answer is negative sine e to the negative 2 minus negative sine, so plus sine of 1. Now, how do I view, for example, 1 what? Sine of 1 what? 1 degree? What is the 1? Anybody want to tackle that one? Because if I wanted to use my calculator and evaluate this, 1 what?
Radian.
Radian. Good. It can only be radians. You can't have degrees because this is a measure. So think like on a circle. If you're finding arc length and things like that, you don't use degrees. You only can use radians because pi radians corresponds to the arc length and things like that. So this would be in radians. So if I wanted to do this on my calculator, it's a piece of cake, but I better be in radian mode. Now, most textbooks will say you can't do that. Write it as 1 over e squared. I'm okay with that. I probably will leave it like that just because it's easier to write and read. Now, can I rearrange it? Can I put the sign? Of course, do whatever you want. But that's a viable answer. Now, I don't need a decimal value, but I need to know how to do the decimal, because if I'm in physics and this represents something, might represent the speed of something or the length of something or the acceleration of something. I'm in chemistry and I need this many milliliters of solution. You got to be able to put it on your calculator. You got to be able to actually correctly evaluate this. So let's all try that. Everybody try to do this on your calculator. So the very first thing I'm going to do is put myself in the proper mode, because the little DRG at the top sometimes is too small for me to read. So I just put it there. All right, so now I'm going to calculate this. Sine 1 and tell me when you got an answer, anybody. Because certainly
0.7065.
beautiful. That means I did it right because I got the same thing. See, if you got a different answer, then I'd assume I did it wrong. So I got, this is, now the proper term is, this is approximately, this is an infinite non-repeating decimal sequence. How many decimals? I don't know. I don't care. How many decimals is really in the situation you're in, what degree of precision is required. And then, by the way, there's no such thing as a right answer to how many decimals. Situations dictate it. I got asked an interesting question yesterday. My 16-year-old son, who's finally starting to think about driving, he hasn't even cared about it. He's starting to think about it. We're stopped in front of a gas station at a stoplight, and he looks up, he knows, he goes, why is it 0.9 cents? It was like 389.9 cents. And he just asked this question about gas. Why is it 0.9 cents? It's not like you can give somebody 9/10 of a penny. And I just laughed. I said, you know, but that's one of the all-time great mysteries. Well, maybe when we learn about, where the pyramids came from, we'll learn about why is there a third decimal place in gas prices. I have no idea why there's an extra decimal place, but it's the idea of when you go to the pump and you're filling it up, it's rounded to the second place because you're paying with money. Technically, it's an infinite non-repeating decimal. When you have gallons and you multiply it by the price, that's infinite. It's a measurement, but we round it to an appropriate place to be able to pay money. Well, how many decimals is irrelevant. What does the situation dictate that you're working with? So if it was 1 place or it was 10 places, you're just rounding it correctly on your calculator. You never are concerned with how many decimals. The situation, when we did Newton's method, right, I'd say, give me a 4 decimal place answer. Give me a 2 decimal place answer. Okay, then that's where I'm going to round it to. It's not that, gee, I wonder what the best rounding would be, because it always depends on the situation. Now, this was ugly as an answer, but fairly simple as a process. And it's the process that I want to get across. So let's keep going. All righty. And how about we throw in a square root this time? How about we do +4? How about we go from 0? All right. Now, without solving the problem, I would like everybody on their own to do the following. I don't want to solve the problem yet. I would like everybody on their own to do this part. Fill this in. What is the u? What is the du? What are my new? What are my new u limits? Okay, let's just take a moment, because it's critical that we're all on the same page, that we all agree that every single part of the process we do exactly the same. This is where we truly want to be like clones. We do not want to be creative right now. Creativity in algebra is not always a good thing. Creativity when you're writing a story is wonderful. All right, let's start with anybody. What's my u going to be?
8x cubed negative 6x squared plus 4.
Good. And again, the reason is not because it's in the denominator, it's more than because it's in the root. So I have it to a power. But when I have a quotient, you know, in the last problem, we had the e came from the denominator, and that was our thing, right? But our function came from the numerator. But when I have a quotient of polynomial-ish things, rational functions, things of that nature, typically the u is going to come from the denominator, because then the chain rule factor almost has to be in the numerator. There are exceptions, but we've kind of gotten used to this, right? What's my du?
24x squared minus 12x.
Is that a problem? And then don't forget, by the way, a lot of times we forget the dx. That's actually important, because this guy here in Calc 1, a lot of people kind of take it for granted. That's actually the most important part of the problem, because that's my instruction. That'd be kind of like if I said, take a derivative. I kind of got to tell you what variable I'm taking it with respect to, because we already know that I can take a derivative with respect to any variable. Here's what I mean. I've got x squared. I'd like you to take the derivative. Well, am I taking it with respect to x or with respect to something else? Because in reality, the farther you go in math, if I said take the derivative of this, it's probably not with respect to x. It's probably with respect to t. So why would it be with respect to t? Because every application you will ever do, this will be a composition of functions. X will be a function of something else. Always. If this is physics, there's no x. There's going to be x of t. So if I said take the derivative of this with respect to x, you'd say the answer is 2x. But if I said take it with respect to t, then it's 2x dx dt. Oh, that matters. So when I write my d whatever, that's the most important thing right there, because that tells me, is this a composition of functions or is this an independent variable? That's not implied ever. It's not implied. Okay, this is a no-brainer, because in Calc 1, these can't be different variables, not in Calc 1. In Calc 3, they will always be different variables, because we'll have multiple independent variables at the same time. So leaving out the instruction means that you don't know what to do next. You know how to do the problem, but you don't know what you're supposed to do, because nobody left the instruction. So now my u, I go to this statement here. When x is 0, u is 4. U is, that sounds terrible English, I know. U is 4. U be 4. When x is 2, I'd have 8 times 8, that's 64. Then minus 24, that's 40. And then plus 4, that'd be 44. Okay, always do a double check there. Now, I don't have exactly my chain rule factor. I have to do some manipulation, don't I?
Factor out 3 over 2.
Yeah, so let's do this first of all. If I factored this, now I don't want to factor out the x, I want to factor out a coefficient. What would be a good coefficient to factor out?
3 over 2.
Well, no, just forget that for a moment. Just look at this. You're ahead of me. You're ahead of me. But if I was going to factor,
Oh.
Four?
maybe,
Four?
maybe a 12.
6. Don't do 6.
Yeah, 12 actually.
I mean, I'm 12 is not a bad starting point, because if I change those numbers, what I'm going to do is create a situation here. Now up here, if I factor out, what I'm trying to get is the same. So if I factor, looks like if I factored out an 8. I'm just trying to make it easier, because if you're thinking too far ahead, there's places I can make errors. So here's the only thing that matters. Those are the same. What I need is a constant multiple of 2x squared minus x. That's what I want you all to see. What I have is a constant multiple of 2x squared minus x. That's it. I have what I need, except that I don't have the right. So, okay, what fraction should I multiply in? What fraction should I factor out? To me, that's way too much thinking. So remember, here's what I showed you guys. Take the 8 and move it out in front. I just removed the 8. Now, what do I need there? I need a 12. So let me insert the 12. Now I just made it 12 times bigger, so I can compensate right here. Does it? Yes, that is 2/3, and that's what you're going to write in your next step. But I don't have to have the 2/3. So if you'd said over here, what should I factor out? Well, that would have been kind of tricky. Technically, yeah, you could have factored out a 3/2, but I'm looking at this. I'm not seeing factoring out a 3/2. That's too much. It's correct, but it's just too much. It's easier if I said factor out the coefficient. Okay, now I've got the same function, different coefficients. So once I did this, that made my life much easier. But before I go any further, here's what I'm going to do next. I'm going to write this as 2/3 integral 0 to 2. And then I'm going to write this to the -1/2. And the reason I'm going to write it like that is because when I do my substitution, that's what my substitution is going to look like. I am never going to have a square root of u in a denominator. There's no logic, because then I got to do another step to rewrite that. I'm going to put it in the form that I'm going to substitute it in. Now, what about my numerator? I'm going to write this times 12 2x squared minus x dx. The original integral and this are exactly the same thing. All I did was I moved this into the numerator with the proper exponent, and I have my chain rule factor, which is now exactly what I need it to be. Now I will perform my substitution. Now, you don't have to do the step I did here, but I think you should, because now it makes the substitution so much simpler and automatic. Because now I can say this is equal to 2/3 u to the -1/2 du. I love that integral. That's going to be easy with these limits. I don't ever go back 0 to 2 for the rest of my life. What most people do, I don't want you to do this at all. What most people will do is they'll go, okay, now I have 1 over the square root of u, but I can't integrate 1 over the square root of u. Now I have to rewrite that in this form. So I'd rather just go straight to this form. So this original problem that looked terrifying has a numerical value that is equal to the numerical value that this problem will produce. But this problem here is not difficult. This problem here is actually pretty simple. So I'm going to get u to the what power?
+1/2.
+1/2. Reciprocal is times 2 times 2/3, 4/3, stop, differentiate. 1/2 times 4/3 is 2/3. Okay, good. And I don't say this joking. I absolutely 100% of the time check my answer right now. I don't check it after I'm all done and then find out it didn't work. No, I'm going to check it right now, because I don't think we're going to mess up the exponent. No, we're more likely to mess up the coefficient. So that's why I quick check. Okay, I got the same thing. Okay, so this is 4/3 times, and I'll go just write it, square root of 44 minus square root of 4. Can I simplify? Can I do anything with this that makes it a little bit better? Anybody?
You just write it as a square root of 40 under the same number and the same route.
Now I can't combine these, but can I manipulate it into one of those individual roots?
Divide all by 4.
Well, how about
Yeah, just 2. Yeah.
do the obvious? Can root 44 be simplified?
Yeah, it's 4 times 11, right? So you could do
Root
2
4
root 11.
11, 2 root 11. I like that. I like that because now you have two choices. You have two choices. Either distribute the 4/3 or factor out the 2. Both would be perfectly good choices. Because I have a 2 on both of these, so either factor out the 2 or distribute the 4/3. It actually doesn't make any difference. So if I distribute, then my answer is 8/3 root 11 minus 8/3. If I choose to factor out the 2, then I'm writing my answer is 8/3 times root 11 minus 2. Now, this would be your choice. But either way, I think leaving a root 4 in the answer seems kind of silly. I actually will have people leave things like square root of 1 in their final answer. Like, isn't that just 1?
I thought that the u was going to be the polynomial.
I'm sorry, I'm sorry, say it again.
I thought the u was going to be the polynomial.
Well, it is.
And then when you make your sub, what did you use as the sub for the u on down there?
We did choose this. This is our u.
Right, but then when you put back in for u, it's
Oh, okay. So at this point, we're evaluating in a definite integral. This is the whole point. This is every part of today's lecture. In a definite integral, you cannot change back to the original variable. There's nothing to change back to. The numerical answer that this produces, we're saying, is exactly the same as the numerical value this produces. So there's nothing to change back to. I just have to evaluate. When we made our substitution, so what is the big difference between a definite and an indefinite integral? In an indefinite integral, because your answer is a function, it should be in the same variable as the question. That's why you substitute back. In a definite integral, your answer is a value. So you're just evaluating something. There's nothing to change back to because your answer has nothing to do with the variable anymore. It's this variable evaluated.
oh, so those become the variables that replace that you're evaluating at.
Limits. Now, if you had, and I don't want you guys to do this in general because it's extra work, but if you were comfortable using computer software, if you had Mathematica or Maple or MATLAB on your home computer, and I'm pretty sure probably you don't, those are extremely powerful. At this point in your life, there would have been no reason for you to ever have these. So maybe you go online, you go to Wolfram Alpha calculator. So you're doing this problem. You get to the end and you get this answer and you're going, I'm pretty sure I did it right. The difference is I can't check this through differentiation because my answer is numerical. So you can use online, I could use an online calculator to check, do I get the same number? The thing is, it won't give you the process. It will, when you're doing online, if you have a graphing calculator and you know how to integrate using your graphing calculator, you can ask this question and it will give you a numerical answer at the end. I would hope it gives you this and not a decimal. It's your graphing calculator might give you a decimal. So then you compare your answer to that and go, okay, I got the same answer. That means my process is probably pretty good. The problem comes when you're trying to do this kind of stuff and using online technology. All you know is when you're right or wrong, you don't know where you went wrong if you are wrong. Does that make sense? So it's like anything else when you're doing it by hand and you quickly use your calculator to check a calculation. Okay, I got the same calculation. Good. I got a different calculation. I have an error. I don't know where my error is. I just know it's not correct. That's the frustrating part. That's like looking up an answer in the back of the book. You got x = 3, and in the back of the book, it says x = 4. All you know is that you're not correct, but you don't know where you went wrong. And that's always the problem is I have no feedback. So I'm doing this problem. I'm pretty sure I did everything right. It is possible to check this answer versus the question. What you're not going to get are the steps. So that's why we're far more interested in the process than the final result. If we get the right answer at the end, to me, that's like, frosting. But if we don't have the right process, we'll never get the right answer at the end anyway. So that becomes a moot point. All right, let's try another one. What if I have something like this? Let's take something truly icky and evil. How about I've got the integral of Now, this one looks kind of crazy. This one, in fact, this one looks almost flat out evil, doesn't it? Does everybody know what this function actually is?
No.
We have the ability to do this, simple substitution.
Is the U just going to be EX here?
That's the
Not exactly,
infinite money
but
formula.
This is actually, it's one of the hyperbolics. This is actually the hyperbolic tangent in E form. Because the hyperbolic sine is half of my numerator and the hyperbolic cosine is half of my denominator. And so the halves would cancel. That's actually, I'm asking you to integrate the hyperbolic tangent, which sounds absolutely terrifying. But in this form here, so Nate suggests that my u be e to the x. That's not a bad choice, but the new integral I'll produce is going to have u's and 1 over u's all over the place. And I don't know if I have a chain rule factor. There's actually a more obvious one. I have a quotient, and normally when you have a quotient, where
Is it the
x,
denominator? The denominator?
how about the entire denominator? Williams suggests that we use the entire denominator. This is a question that every calculus book will sneak in, mostly just to scare you and make the authors feel superior. What's the derivative of this?
Negative e to the x plus e to the negative x.
Well, same for this guy, right? This is
Yeah, that one's just e to the x.
How about this one?
Negative e to the negative x.
Now, why is that a good thing? So this integral is going to end up being what? Just 1 over u du. Oh my gosh, you got to be kidding me. It's going to be that simple? Yeah, this one's actually going to be very simple, but I had to recognize the relation with the e's. Now, what about the limits? X is going to range from 0 to 1. Now go back, by the way, don't look at this. Look at this. Look at very specifically, what did you call your u? You called your u e to the x plus e to the negative x. So if I replace x with 0, I have e to the 0 plus e to the 0. What is that?
2? Because they're
E to the 0 plus e to the 0 is 2. Now, replace x with 1, and I'll have e to the first plus e to the negative first.
0? Wouldn't that be backwards then?
No, e to the first plus e to the negative first, or 1 over e if you'd like. No, it's definitely not 0. I'm adding things. So I could write it as e plus e to the negative 1, or I could write it as e plus 1 over e. It doesn't really matter. But now when I do that, this is already perfect du on top. So this is 1 over u du. I love this. That's one of my favorite integrations. Hard to mess that one up. And I'm going from lower limit is 2, upper limit is e plus 1 over e. Now, there's no part of the process from this point on that should trouble us. Okay, so I'm going to get natural log absolute value of u. I don't even have a coefficient to concern myself with, from 2, and then e plus 1 over e. Now, here's where sometimes people get in trouble because they're not sure about log rules. So let's just evaluate this first. So I'm going to have, this is a positive number, so I can drop the absolute value. Okay, so far, is everybody happy with that? It's ugly, but are we happy with this as an answer so far? Anybody?
Yeah.
Yeah, it's correct. Now, the question is that the best answer I could possibly give? That's a tough question. It's correct. And if you are not absolutely comfortable with logarithms, I would say just wave at this and walk on. But it may be possible that I can simplify this, that I can do things. It might be possible. It's always possible. Whenever you have a log, it's always possible to keep going. We did it earlier, but is it efficient?
Is it because it's subtraction? You can write this as a division.
Well, we got the sum of logs, no?
Here's the number one error people make. Now, here's something we know. Log A plus log B is log AB. The sum of the logs is the log of the product. And we know log A minus log B is the log A over B. We know that. Question, if I have log of A plus B, is that equal to something? The sum of the logs is the log of the product. The difference of the logs is the log of the quotient. That's an absolute log rule. Is there anything I can do with these? Yes or no? Log of a sum, log of a
Is
difference.
the ln A times ln B? Or
These are the rules. Can I do anything with these?
No.
no?
No.
No, but do we want to? Oh,
Yes,
so
please.
bad we want to. Why do we want to? Because we look at this and we confuse it with this. And I want to make sure everybody understands these are laws. These are easy to prove. There's nothing I can do here. But because sums and logs, what will people do? They'll try to pull it apart. You can't do that. You can't do it. I can't do anything with that in terms of the fact that there's a sum. There is no log property. But I can do something with this. For example, E plus 1 over E. Can I make that into one quotient?
E over E.
So I can multiply that by E over E, making this. Is that true? Oh, I'm sorry, plus.
Yeah.
Algebra, yeah. So, okay, let's start with that. Then I can say this is E squared plus 1 over E minus log 2. Now, William made the suggestion, difference of logs, log of the quotient. So at this point, can I write this as that?
Yes.
Yes. Now, I don't know if you would say this answer is superior to this answer, but this is a log of a quotient, so I could actually also write this as, in other words, I can move that E over there. Difference of logs, log of the quotient, or just leave it alone. So I would say this, they're all equal. But if you don't see a huge advantage, which one should you leave it as? Or which one should you do?
The original.
The original. I'm a big fan of leaving it alone if you're not certain or if you don't gain an advantage, because you might make a mistake. You did perfect calculus to get here and then goofy algebra. Okay. Now, are there times you should simplify? Oh, yes. Yes. And you're going to find this is a very common thing with logarithms. So let's suppose we got to the end of the problem, because I want you to understand logarithms are huge. The question comes up all the time with me, and as a department, people will ask me, what do you need your calculus students to know from pre-calculus? Do you know what I always tell them? I don't tell them trig. The number one thing I want my pre-calculus students to know when they walk into calculus, logs. And that's the one thing almost all calculus students say, yeah, we did not spend enough time on logs in my previous classes. So you get to calculus, and you can do the calculus of logarithms, but we don't do well with the algebra of logarithms. And that's the thing I need people to know well. In chemistry, do you use logs? Yeah. In physics, do you use logs? Yeah. In calculus? Yeah. So if I had something like this, let's say I got to the end of the problem. Okay. Okay, I got to the end of the problem, and this is what I had. Everybody okay with that? We're good? Can I do better? Can I do better?
ln5.
Yep, and that is better. The difference of the logs is the log of the quotient. We know this, but we don't always do it. See, we said this is totally okay to leave it alone because is this really, this is equal to this. But is that some simple thing to work with? Or is that, we had to do some serious algebra to get there. Well, okay, not that serious, but we had to do some algebra. The question is that really way better? I don't know. I mean, it's an opinion. Is that really way better? Yeah. I'm doing log of a single integer. So the simple rule of thumb that I like to follow is when you have a difference of logs, you know it's the log of the quotient. But it's really only an advantage if that quotient reduces to an integer. If that was a 14, then this would be log of 14 thirds. That would be a correct answer. But is that an advantage? to do the log of a fraction, because think about entering it into your calculator. Which is easier to enter in your calculator, the difference of logs of integers or the log of a fraction? Which is easier to enter?
Integers.
The integers, because the log of a fraction, first of all, you have to use your parentheses. Oh, and we sometimes forget to use the parentheses. And if I screw up the parentheses, I will get a completely unrelated answer. You know, there's things involved. This is the one time I say, no, you always simplify the log when that's going to produce an integer value. That's the rule of thumb. The difference of logs is the log of the quotient, but I only take that advantage if it reduces to something easier to work with. That's all. Now, might it be that it didn't reduce to a fraction? Again, I want to show this because this comes up a lot from this point on because we work with logs. What if I had this? Let me go back to this statement here. Let's say we had something like this, and maybe it was, I don't know, let's say that's what we had. So this is log 44 minus log 8, and that is the correct answer. But when it comes to logs, we really like our numbers to be smaller, if possible, just easier to work with. Is this correct?
Yeah, looks good.
Can I do anything with that?
11/2.
Ooh, that's way better. But it's still not an integer.
Ooh.
These are all equal. That's probably the only one I wouldn't want to go with, because this is equal to this. If you're going to leave it as a difference of logs, how the heck did we do that? Yeah, we did that. Isn't that crazy? Because of this property. Now, a lot of you would argue, you know what? I'm okay with this. 11 halves. Like that, I'm okay writing 11 halves. By the way, you don't have to do anything at all. But the fact is, this does reduce. It reduces a lot. So again, that's simply being comfortable with logarithms. Okay. And logarithms are really, really big in what we're doing, the nature of the problem. Now, no one's looking at this and seeing the log, but what you are doing is noticing the derivatives and you're seeing the results sitting up there. All right, so let's keep going. Let's keep going, shall we? I'm not doing all of the antiderivatives today. I'm going to reserve like the inverse trig and some of the ickier, logs of trig functions. I'm going to reserve those for the next class, just so we're going to practice really the algebraic ones today, the ones that are just not that taxing. All right, so now I'm going to give you a problem. Everybody's going to do this one. Let's say we've got 3x squared minus 2x. And let's say we're raising this to the 4th power. It's 9x minus 3. And I want to go, let's keep it simple. We're going to go from 1 to 2. All right. I would like everybody on your own. So I'm going to stop recording for a minute. Okay. Now let's go to it. So I know, Gil, you are the furthest along. So what's my choice of u? And again, it should be easy, but when you see a product of things, sometimes we go the wrong direction. So what should my u be?
3x squared minus 2x.
3x squared minus 2x, which makes the du pretty simple. That's 6x minus 2 dx. But that's not exactly what I have. So what would a good idea be? Go again, think about what fraction. Factor it.
Yeah.
What factors?
2.
2 times 3x minus 1. And then I go back to here. This
3.
is 3 times 3x minus 1. And this is a good thing, isn't it? Because that means that what I need and what I have are both multiples of 3x minus 1. That's a good thing. So I need it to be a 2. I have a 3. So hopefully everybody has something looking like that. Now, last piece of the puzzle before I continue in the problem. What are my new limits of integration?
I said 1 and
1 to
4.
1 to what?
I said 1 to 4, but
I
might
said
be
1 to
wrong.
8.
Well, let's see. 3 minus definitely 1. 3 times 2 squared minus 4, that should be 1 to 8, I believe. That will make a difference at the end of the problem, but not in how you do the problem. So you can just fix it later. But yeah, it brought up a good point here, is that you got to be careful that you got those numbers right. Just like any definite integral, if I evaluate it incorrectly, I'm going to get a wrong numerical answer. Now, I can now substitute directly. And absolutely all substitutions, whether it be a definite or indefinite, you do all of it at one time. You don't do it in stages. So I'm going to have what? What is my new integrand?
U
Everybody.
times du.
U? About
Sorry, u fourth.
to the
Sorry,
fourth, yes. And from 1 to 8. And again, what we're saying is whatever the original problem produced as a numerical value, my new integral will produce exactly the same numerical value. That has to be an absolute money-back guarantee, because if you can't guarantee this produces the same answer as this, then what would be the point of finishing the problem? If I can't guarantee I'm right, then I'm just going to do stuff at the end and say, gee, I hope this went in the right direction. No, I'm guaranteeing you this is going to produce the same answer. Again, if I can't guarantee it, then I'm just saying I'm guessing from here on out, and I don't want to guess. All right, so my antiderivative is what?
un plus 1 over n plus
No.
1.
No, I don't want a formula. I want an answer.
Oh,
There's no ends in the problem. What's the answer? What's the antiderivative? Come on, you guys have already done the problem.
It's 1 over 5 u to the 5th. But then you take the 3 over 2, so it's 3 over 10.
There we go. Okay, that's what I'm looking for. Yeah. Don't quote me a formula. That doesn't help me. I want the answer from 1 to 8. Now, I need my calculator at this point. So how about 8 to the 5th minus 1 to the 5th? This is what I'm going to write down. I don't need to calculate this, subtract them, multiply them by 3, then divide them by 10, then to reduce the fraction. I kind of laugh at that. I would hope everybody at this point uses one of these and just enter it left to right. So the answer is 98,301 tenths. That's it. Now, do we all get that? Just holler out if you got it. See, everyone should be going, of course I got it.
Yeah, got it.
Now, that's a big answer. Why is that answer so big? Because look at your integrand. If I actually multiplied this out, I'm not going to, but if I multiplied this out, my integrand is a 9th degree polynomial. A 9th degree polynomial, which means my antiderivative is a 10th degree polynomial. I'm taking x to the 10th power and evaluating it from 1 to 2 if I had actually multiplied it out. That's why my answer is so big, okay? Because 2 to the 10th power is 1,024. This answer here is over 9,800. Okay, that makes sense. I'm in the thousands. So now, using the logic that I just said, I have a 9th degree polynomial. Oh, and by the way, with a lead coefficient of 3 to the 4th times 9, that means I have a lead coefficient of 729. So my lead term is 729 x to the 9th power, and I'm going to integrate that. Of course, I'm going to get a huge answer. If I had gotten a small answer, I would have been suspicious. A lot of you get suspicious for the big answers. No, I actually should expect a big answer in this case. Now, we could do these all day, but it's all the problems are going to keep looking the same. Most of you have done an excellent job right now with your substitution. In fact, when I'm looking at your quizzes last week, they look like my answer key. Step by step, looks like you guys got into my files and just copied everything down. That makes me feel very good, because it means we're like-minded in how we're doing things. Now, you may just be going, I looked at the notes and I'm just trying to imitate everything you did. That's a good way of doing things. Just imitate the way I did it, but also understand it every step of the way. Why am I doing this step? Why am I doing it this way? In this process, this has become somewhat routine. Getting the correct coefficient, it doesn't involve cleverness, but I have to get this right. So forget the limits for a moment. Last week, everybody could convert this original problem into this problem, 3/2 u to the 4th. The only difference is we're taking the limits of integration and putting down the limits that go with that particular substitution. So then evaluating the problem isn't that complicated. And I have a calculator. I don't need to do this pencil and paper. Okay, so from this point, boom, boom. Heck, technically, you could even go from there to there. I would probably write this down. That way I have something I can check, because a lot of times I can make a misenter on the calculator. So I always want to make sure that I have a nice trail of breadcrumbs here to follow. Now, this is going to require practice. Okay, some folks here practice a lot of homework. Some folks try to get this without practicing any. This should be the thing you practice more than anything else you did this entire semester, because of all the things you learned in this class this entire semester, this is number one. Substitution in general is the most important concept. Substitution of a definite integral is number one. It's your royal flush if you're a poker player. It is the single most important skill that you leave Calc 1 with. The inability to do this means that you won't get the right answers to integrals in general, because after this class, it's understood that you're probably doing some form of substitution in your integral pretty much every time you integrate. That's just the way it works. And if I can't guarantee my numerical answers correct, then I'm doing problems partly correct, but I'm never getting a right answer. And that's no good. I want to be right every time, and I don't want it to be taxing. Now, you never formally have to change this if you choose to do the general antiderivative first and then come back. That's always legal, like I said, but it's the most amount of work you could possibly do. And so I'm showing you this because this gets me through the problem in about half the steps, and I'm still going to get the same answer. But the work I'm doing is actually much shorter and much simpler. So I want you to know this and the original, which again, the original is find the antiderivative of this as a function of x, and then evaluate that antiderivative of a function of x at 1 to 2. And of course, when I do that, I better get this answer. Otherwise, something went wonky. Okay, so let's stop there.